Hi everyone, today's class reviews the principles that govern the chemistry of cells, and some of these principles are things you already know. So this will be more like a review of the material you learn in general chemistry. Today's class will cover these basic principles, in particular the importance of carbon, water, and selectively permeable membranes, and the synthesis of polymers from small monomeric subunits, and finally the principle of self-assembly. Carbon is considered the most important element in biological macromolecules, though it is not the most abundant element in cells. It is not carbon but hydrogen that is the most abundant element in cells, in part because cells are approximately 70% water. But carbon is what forms the backbone of biological macromolecules, and this is why it is considered so important. When we think of carbon, we think of organic chemistry, and people typically think that organic chemistry is synonymous with biochemistry. But they're not the same thing because organic chemistry is concerned with the chemistry of carbon-containing molecules, and those could be natural compounds, but they could also be synthetic. Biochemistry or biological chemistry, on the other hand, refers to the study of the chemical and the physical processes that occur in cells. The fact that carbon is the most important atom in biological macromolecules stems from its properties. Carbon has a valence of 4, and recall that the valence of an atom is the number of bonds that is able to form, which is based on the number of electrons in its outer shell. Recall that for all atoms except for hydrogen, the outer shell is filled when it has 8 electrons. Now, carbon has 4 electrons, as you can see here, so it needs another 4 electrons to have a filled outer shell. And atoms are most stable when their outer shell is filled. So this means that carbon can form up to 4 covalent bonds. Recall that covalent bonds involve the sharing of electrons between atoms, and carbon typically forms covalent bonds to other carbon atoms, but also to oxygen, hydrogen, nitrogen, and sulfur. As previously mentioned, carbon can form up to 4 single covalent bonds, and in single covalent bonds, like the ones shown in these molecules, there is a sharing of a single pair of electrons between the atoms that are forming the bond. Because of its valence, carbon can also form double bonds where 2 pairs of electrons are shared between atoms, or triple bonds where 3 pairs of electrons are shared between atoms. Whether carbon atoms form single, double, or triple bonds, the total number of covalent bonds per carbon atom is going to be always 4 because the valence is 4. And we're going to encounter mostly compounds that have single and double bonds, since triple bonds are rare in biological macromolecules. Because the bonds present in carbon-containing molecules are covalent, they're stable, and that stability comes from the high bond energies of these carbon-containing covalent bonds. What you're seeing in this graph are the bond energies of different covalent and non-covalent bonds. For single bonds, you can see that the bond energies are between 70 to 100 kilocalories per mole, and the bond energies are higher for carbon-containing double and triple bonds. If you compare that to hydrogen bonds, which are non-covalent, you can see that the bond energy for the hydrogen bonds is much lower. By the way, you do not need to remember the numbers that I'm saying here, just the relative differences among the bond energies between covalent and non-covalent bonds. Now, bond energies tend to be a point of confusion for students because sometimes there are misconceptions about bonds. Keep in mind that bond energy is not the amount of energy stored in the bond. Bond energy refers to the amount of energy that is needed to break the bond, because breaking bonds requires energy, and the formation of bond releases energy. And this is where the misconception is rooted. And at this point, you may be saying to yourself, wait, but doesn't the breakdown of ATP to ADP and phosphate release energy. Well, yes, that's true, but it's not because a bond is being broken per se. It's more because of how the bond is being broken. More specifically, the reason this reaction releases energy is because it is an exergonic reaction. Now, why is this reaction exergonic? We're going to talk about the specific reasons why the breakdown of ATP is exergonic later in the semester, but for the time being, bear in mind that the breakdown of ATP, which occurs through a hydrolysis reaction, and this is a reaction where the addition of a water molecule is used to break a bond, this reaction involves actually both bond breaking but also bond formation. Bonds form between phosphate and an oxygen from a hydroxyl group that comes from the water. And bonds also form between the ADP and the hydrogen from the water, but the hydrogen is lost to ionization. Additionally, the fact that this reaction is exergonic results both from energy that is released by bond formation, so changes in enthalpy, but also by the fact that there is an increase in entropy. And as I mentioned, this is something that we're going to talk about in more detail later in the semester, so I'm not going to elaborate on this any further at this point. So once again, that bond energy refers to the amount of energy that's needed to break a bond. So as you can see, this bond energy for carbon-containing covalent bonds and even for hydrogen bonds is higher than the thermal energy or the vibrational energy of molecules, which results from the random movements of molecules. So this means that those vibrations cannot break these bonds. The stability of carbon-containing bonds is also important when we consider the visible light spectrum. This graph shows you energy on the y-axis and wavelength on the x-axis. So the line shown here in purple is the relationship between wavelength and energy. And as you may know, the shorter the wavelength, the higher the energy. So as you can see, UV light has greater energy compared to visible light. Superimposed on this graph are the bond energies of various carbon-containing covalent bonds. And as you can see, the energy of visible light is lower than the bond energies of these carbon-containing covalent bonds. So this means that visible light cannot break these bonds, and this makes life on Earth possible. This graph shows us that the amount of energy of UV light, which is around here, is greater than the amount of energy of most of these carbon-containing covalent bonds. So that means that these bonds can be broken by UV light. This is why you could use UV light to disinfect a surface, as it can kill microorganisms. Now, this is also the reason you should avoid prolonged exposure to UV light, because this could damage DNA and result in mutations that could increase your risk of developing skin cancer. So those gel manicures that require UV lights to cure may not be such a great idea after all. Another property of carbon-containing molecules that makes them well suited for life is the fact that they're very diverse, and that's because carbon can form, as we said before, up to 4 single covalent bonds. Now, despite that, there are many molecules that are composed mostly of carbon and hydrogen, like fatty acids. Molecules that are composed only of carbon and hydrogen are known as hydrocarbons, and these hydrocarbons are hydrophobic because the carbon-hydrogen bond is nonpolar. And the reason this bond is nonpolar is that the electronegativity, or the attraction for electrons of carbon and hydrogen, is similar. So they have an almost equal share of the electrons. Now, since these hydrocarbons are nonpolar molecules, they're not soluble in water and they're not very reactive. Despite that, the molecules that are composed mostly of carbon and hydrogen include lipids, which are extremely important in cells. So they're not only part of the cell membrane, but they are also used as a major source of energy storage in some organisms. And they also play roles in cell communication, since there are hormones like estrogen, testosterone, and cortisol that are derived from cholesterol. Many biological macromolecules have the functional groups that are shown here. And recall that a functional group is an arrangement of atoms that has specific chemical properties. Now, these functional groups are hydrophilic. For example, the carboxyl, the phosphate, and the amino group are all ionized or charged at physiological pH. The other groups, the hydroxyl, the sulfhydryl, the carbonyl, and the aldehyde, are not charged, but they're hydrophilic because they contain polar bonds. Because these groups are polar, they are soluble in water and they tend to be more reactive than hydrocarbons. These functional groups are polar because there's an uneven sharing of electrons between the atoms in some of the bonds of those groups, resulting from differences in electronegativity in those atoms. This periodic table of elements shows the elements color-coded by electronegativity, where the purple is the least electronegative. So these elements have the lowest attraction for the electrons, while the elements that are shown in the bright pink, like oxygen, fluoride, and chloride, have the highest attraction for electrons. In simple terms, if you have a covalent bond between an oxygen, for example, and a hydrogen, so if you have a hydroxyl group, we can see that these atoms have very different electronegativity. So the oxygen will have a greater attraction for the electrons than the hydrogen, and that makes the bond polar. In order for a bond to be polar, the atoms that make up the bond need to have different electronegativities. So a bond between two highly electronegative atoms, like two chlorides, is a non-polar bond since the electrons are shared equally between the two atoms. In addition to differences in electronegativities, the geometry of the molecule is also important for bond polarity. And I'm not going to discuss this in detail because it's not something we're going to encounter frequently. But for example, if the water molecule was planar as opposed to bent, then the dipole moments would cancel out and the molecule, even though it has polar bonds, would not have polarity overall. As you'll see, differences in electronegativity also influence the oxidation state of carbon. And the oxidation state of carbon is really important because it's relevant to the amount of energy of carbon-containing compounds. Just as a reminder, oxidation is the loss of electrons and reduction is the gain of electrons. So remember the mnemonic that you probably learned in general chemistry, oil rig. Oxidation is loss, reduction is gain. In this diagram, the molecule that is labeled A is a reducing agent, so it becomes oxidized as it donates electron to the B molecule, which becomes reduced. And remember that these types of reactions happen together. These are known as redox reactions because a reduction is always coupled to an oxidation. In carbon-containing compounds, this redox reaction occurs so that both the electron and the proton are transferred. So this is basically a transfer of hydrogen. So when we look at carbon-containing compounds like the ones shown here, if we're looking at the relative oxidation state of carbon, what we're looking at is whether the carbon is bonded to hydrogen or bonded to electronegative atoms like oxygen. When the carbon is bonded to hydrogen, a carbon is said to be in a more reduced state. The reason for that is that although a carbon-hydrogen bond is nonpolar, as you can see from this electronegativity table, the carbon is slightly more electronegative than the hydrogen. So the carbon has a greater pull for the electrons. So methane, which is composed of 4 hydrogens bonded to a carbon, is more reduced than carbon dioxide, which is the most oxidized form of carbon. Biological macromolecules that are more reduced, like fats, have greater energy than those that are more oxidized, like carbohydrates, which have all of these hydroxyl groups. Now, this is because more energy can be extracted from a compound that is more reduced by oxidizing that compound, as opposed to the amount of energy that can be extracted from a compound that has carbons in a more oxidized state. So more energy in the form of high energy electrons can be harnessed by oxidizing a fat as opposed to oxidizing a carbohydrate. The last property of carbon-containing compounds that we're going to discuss is their stereochemistry. But don't worry, I won't get into a lot of detail here since this is not a biochemistry class. Stereochemistry simply refers to the fact that there are compounds that have the same chemical formula and the same structural formula, so the atoms are bonded to each other in the same order, but they have different configurations. So that means that the arrangement of atoms in space is different. When we consider carbon-containing compounds, because a carbon can have 4 different groups attached, these compounds can exist as stereoisomers as long as there are 4 different groups attached to a carbon. When that is the case, the carbon is said to be asymmetric or chiral. So when a molecule has one or multiple chiral carbons, it can exist as stereoisomers, and some of those stereoisomers, like the example shown here, can be mirror images of each other. When a molecule has multiple chiral carbons, it can have multiple stereoisomers, but obviously, not all are going to be mirror images of each other. For example, glucose has 4 chiral carbons, and so it has 16 stereoisomers. And the formula to figure out how many stereoisomers you can have for a chiral compound is 2 to the n, where n is the number of asymmetric or chiral carbons. So of the 6 carbons that are present in glucose, not all of them are asymmetric because not all of them have 4 different groups attached. For example, carbon 2 is a chiral or asymmetric carbon because it has 4 different groups attached to it: a hydroxyl, a hydrogen, an aldehyde, and then this entire group over here. On the other hand, the aldehyde, the carbon that's present in this aldehyde, is not a chiral carbon because there are only 3 different groups attached here as opposed to 4. Now, going back to the number of stereoisomers, for each asymmetric carbon, there are 2 possible configurations. So the total number of stereoisomers for glucose is 16, 2 to the power of 4. That doesn't mean that the 16 stereoisomers are mirror images of each other. Obviously, logic tells us that that would be impossible. When we look at some of the stereoisomers of glucose, as you can see, some are mirror images of each other and some are not. The compounds that are mirror images of each other are known as enantiomers, and I'm going to write that down, but you don't have to remember that. Now, the enantiomers are designated as D or L, and this is a way of naming isomers by relating them to the molecule glyceraldehyde. And I'm not going to ask you to remember this since this is not a biochemistry course or an organic chemistry course. But the important thing to see here is that when you look at the stereoisomers of glucose, you have some stereoisomers that are not mirror images. So mannose, D-mannose, is a stereoisomer of D-glucose. They have the same chemical formula. They also have the same structural formula since the atoms are attached in the same order, but they differ in the configuration of one of their chiral carbons. Now, the important take-home messages are that in order for a carbon-containing compound to exist as stereoisomers, it must have at least 1 chiral carbon, and remember that a chiral carbon is a carbon that has 4 different groups attached. Additionally, stereoisomers, particularly those that are mirror images, can have very similar chemical properties and sometimes even identical chemical properties, but they then have different physical properties and they can have very different biological properties. And I'm going to show you an example of that in a moment. Also, there are differences on the ways in which stereoisomers are utilized by cells, as we'll see when we talk about amino acids next week. For example, these 2 drugs, Darvon and Novrad, are stereoisomers. Specifically, they're enantiomers, so they're mirror images of each other. And these are real names. I'm not making up these names. Now, Darvon is a painkiller, while Novrad is a cough suppressor. So the reason these stereoisomers have these very different biological effects is that enzymes are stereospecific, and I'm going to write that down because that's really important. So what I mean by that is that an enzyme, the active site, is specific for a particular stereoisomer. This is why these drugs, even though they have the same chemical formula, the same structural formula, they have different biological effects based on their stereochemistry. Another example of the importance of stereochemistry is the drug thalidomide, and this is a drug that was used in the 50s to treat morning sickness during pregnancy. And it was found to cause birth defects, so it caused limb defects and also ear defects. Now, in these figures, the R and the S, this is just a different way of naming stereoisomers. For thalidomide, the R enantiomer was effective at reducing the symptoms of morning sickness, whereas the S enantiomer was the one that caused the birth defects. However, in the body, these enantiomers for thalidomide can actually be converted. So the R enantiomer can be converted to the S enantiomer once ingested. And because of that, even if someone were to take the pure R enantiomer, it's possible that they could still have a child with birth defects. So as you can see, understanding stereochemistry and how certain enantiomers behave in the body is really important.